Hi everyone, this is the lecture number 9 on the statistical methods in the high energy physics. In the previous video, you've seen a pretty cool way how to find estimators for unknown parameters of your models. In a nutshell, you take a joint probability density function from which the whole dataset was sampled. You insert your measured dataset and get the likelihood function, which you treat formally as a function of the model parameters. Then you find its maximum in the parameter space. The position of the maximum corresponds to the maximum likelihood estimator. Amazingly simple, isn't it? And how fascinatingly it works. Moreover, you haven't heard the best thing yet. Let me say it right now. The maximum likelihood method always gives an efficient estimator if it exists. Recall that an efficient estimator has the smallest variance allowed by the Rao-Cramér-Fréchet bound. Furthermore, the maximum likelihood estimators are almost always efficient in the large sample limit, except for some rare situations. The best thing at the end. Maximum likelihood estimators are normally distributed in the large sample limit. And a bonus, the likelihood function itself, evaluated at any value of the parameter, is also distributed normally in that limit. This video will be about various ways how to estimate the variance of maximum likelihood estimators. The variety of the variance estimators is quite large. We will describe 4 approaches: Analytical Method, Monte Carlo Method, application of the Rao-Cramér-Fréchet's minimal variance bound, and Graphical Method. Let's start with the Analytical Method. The Analytical Method can be used just in the simplest situations. Analytical means that we just calculate the variance explicitly according to the formula defining the variance. We've shown how this works in one of the previous videos. In that video, we have calculated the variance of an arithmetic mean of some measured values. Now, we just add that the arithmetic mean is the maximum likelihood estimator of a normal distribution mean value. As a reminder, let's write it down again. Variance of an estimator of the mean of Gaussian distribution, mu hat, equals to sigma squared over n, where sigma is the value of the Gaussian width and n is the number of measurements. We've just demonstrated that for a simple example of the normal distribution, we can calculate the variance of the estimator of mu explicitly and exactly, without using any kind of approximations. Let's gamble now with Stanislav Ulam's uncle in Monte Carlo. Well, not really with his uncle, but rather with Stanislav Ulam himself. This type of gambling is becoming more and more popular with the rise of computing resources. Monte Carlo is often viewed as a brute force way of achieving goals in statistics, in the sense that the methods can be computationally very demanding. On the other hand, it gives us very precise results if we generate enough events, to say if we can afford paying the electricity bill. Let's look at how people use the Monte Carlo method to estimate the variance of the maximum likelihood estimators. Let's assume we've just measured n values xi. For example, we milked n cows and measured the amount of milk each time. Each milking was effectively just sampling of a value from a probability density function f of x with parameter theta. I don't dare to say what the parameter theta could be and how the statistical model f of x theta could look like. Most probably a normal distribution as always, but I am definitely not a farmer. Anyway, let's assume that some experienced farmer told us what the model was, and we estimated the parameter theta for him with the use of the maximum likelihood method. Given that this video is of a Czech origin, we can call this farmer Andrew. Either he is rich and can afford to pay the large electricity bill, or the PDF he gave us is so unusual In any case, he told us to use the Monte Carlo method to estimate the variance of the estimate theta hat. Simply, we do a large number of milking pseudo-campaigns. Let's call this number capital N. In each pseudo-campaign, we pseudo-milk the same number of pseudo-cows as was the original number of cows that we really milked. We call the number N. Each pseudo-milking is just a generation of a random number from the probability density function f of x with parameter theta hat. Note that we have to use some concrete numerical value of the parameter theta, obviously, and it's very natural to use our estimate of the parameter. In summary, we have now capital N of pseudo-dataset, and let's denote the kth pseudo-set as x vector k. For each pseudo-set, we evaluate the value of the maximum likelihood estimator. Let's call this value theta hat k. Finally, the variance is very easy to estimate. Estimate of variance of theta hat equals to 1 over capital N times sum, k going from 1 to capital N, of theta hat k minus theta hat squared. This estimate is unbiased because the parameter theta hat is the same as we used in the probability density function when generating the pseudo-data. Alternatively, we can use the mean value of pseudo-estimates theta hat k instead of the original estimate theta hat. However, in this case, we would have rather used the factor 1 over n minus 1 in order to get an unbiased estimator of the variance. A completely alternative way how to generate a large number of pseudo-datasets is called the Bootstrap Method. This method relies just on the measured dataset. A pseudo-dataset, x vector k, is generated in the following way. For each event from the measured dataset, we generate a random number w according to a Poisson distribution with the mean value equal to 1. Then, we take the event and we insert it w times into the pseudo-dataset we are preparing. This means that the original event is either skipped or used once, twice, 3 times, etc. Obviously, the number of events in the pseudo-dataset x vector k is no longer equal to the number of measured events. We can nevertheless use the pseudo-dataset to estimate the value of theta, thus getting an estimate theta hat k. Then, for the variance estimate, we use the same formula as before. A great advantage of the Bootstrap method is that it preserves potential correlation in the original data. Let's say that apart from the amount of milk, we also measure the amount of hay each cow eats before the milking. So each measurement will consist of 2 numbers instead of just 1. There for sure will be a correlation between them, because more the cow eats, the more milk she produces. At least that's what I, a guy from a city, would assume. Because the Bootstrap method is just reweighting of the original data, any correlation which was there will be preserved. In contrast to the Monte Carlo, there is a method that boils down to a very cheap recipe from the computing point of view. It is based on the work of gentlemen Rao-Cramér-Fréchet, who derived a formula for a minimum variance bound of any estimator. These 3 guys were very smart and derived the bound in general, even for biased estimators. However, we won't profit from their whole effort, because the calculation of a bias is often not possible. Anyway, the assumption of zero bias is almost always made when estimating the variance of our estimators with the use of the Rao-Cramér-Fréchet minimal bound. In case of doubts about the zero bias assumption, one can, for example, do a check with the use of a Monte Carlo method. Here we go with the magic trick. Sure, you guessed it. The covariance matrix of our parameter estimators is approximated by the Rao-Cramér-Fréchet bound. Mathematically, V sub ij equals approximately to inverse to I sub ij. The Fischer information matrix I is defined by the following expression. I sub ij equals to expectation value of minus second derivative of log of joint of x vector theta vector over d theta I d theta j and this equals to integral of minus second derivative of log f joint x vector theta vector over d theta I d theta j times f joint x vector theta vector dx1 to dxn. Typically, you will find this definition using the likelihood function instead of the joint probability density function. However, we really want to stress that we integrate over the data space. Therefore, the Fischer information matrix does not depend on the actual observed dataset. Unfortunately, the integration might be a very difficult task. A commonly used estimator of the Fischer information matrix replaces the mean value by evaluating the argument for the maximum likelihood estimator theta hat. I hat sub ij equals to minus second derivative of log L by d theta I d theta j evaluated at theta vector equal to theta vector hat. Note that we use the likelihood function here. The likelihood has the measured dataset encoded, and therefore this estimator of the Fischer information matrix depends on the observed data. If we have just the one parameter of interest, then the formula reduces to the following one. I hat equals to minus second derivative of log L by d theta squared, evaluated at theta equal to theta hat. The variance estimator of theta hat is then estimator of variance of theta hat equals to minus 1 over second derivative of log L by d theta squared evaluated at theta equal to theta hat. And this we write down as a sigma squared sub theta hat. You might have got an impression that there are too many approximations involved already. Replacement of the covariance matrix by its minimum bound, assumption of zero bias, estimation of the Fischer information matrix with the observed data. Let's address these worries briefly. Mostly, you don't need to worry, provided that your measured dataset is sufficiently large. In particular, the estimator of the Fischer information matrix works very well in the large sample limit. You should also recall that the maximum likelihood method finds efficient estimators if they exist, and they exist if we have large enough dataset. What concerns the assumption of zero bias, if you are in doubt, you can always check the bias with some Monte Carlo technique. Actually, the approximation of the covariance matrix using the presented estimator of the Fischer information matrix is largely used in particle physics. For example, routines Migrad and Hesse and the minimizer Minuit 2 use it. Minui2 is minimizer package used in the data analysis framework root. Let's close the chapter on the variance of the maximum likelihood estimators by reviewing the one last method. The graphical method is a very elegant way of the variance estimation. It has a lot in common with the previous method that was based on the Rao-Cramér-Fréchet minimal variance bound. If we have a large measured dataset, then the two methods are equivalent. The graphical method builds on the fact that the distribution of maximum likelihood estimators is Gaussian in the limit of large dataset. Let's see how the method works step by step. Once again, we will not consider biased estimators. First, we expand the likelihood function around the point theta vector hat, where its maximum is located. We will use the symbol delta theta vector to denote the line segment theta vector minus theta vector hat. The Taylor series for the likelihood functions looks like this. Log L of theta vector equals to log L of theta vector hat plus delta theta vector, and this equals to log L of theta vector hat which equals to log L max plus sum over k of derivative of log L theta vector by d theta k evaluated at theta vector equal to theta vector hat times delta theta k plus 1/2 of double sum over ij of delta theta I times second derivative of log L theta vector by d theta I d theta j evaluated at theta vector equal to theta vector hat times delta theta j plus higher order terms. Obviously, the first term is just the maximum value of the likelihood function. The second term is a function of the gradient of the likelihood. It's clear that the gradient is 0 at the function's maximum. The third term contains the estimate of the Fischer information matrix that we've shown a short while ago. So the second term equals to minus v hat inverse sub ij. We use the Fischer information matrix as an estimator of the inverse of the covariance matrix. Finally, we neglect all higher terms of the Taylor series. Therefore, we can rewrite the formula as follows. Log L of theta vector hat plus delta theta vector is approximately equal to log L max minus 1/2 of double sum ij of delta theta I inverse of the estimate of covariance matrix sub ij times delta theta j. If there is just one model parameter theta, then this expression reduces to a formula describing a parabola. We have log L of theta hat plus delta theta equal to log L max minus delta theta squared over 2 sigma hat theta hat squared. Then, if we choose delta theta equal to plus minus sigma hat theta hat, we are getting very well-known expression. Log L of theta hat plus minus sigma hat theta hat equals to log L max minus 1/2. In situations when we have a large data set, this formula gives us a simple prescription how to find the 68.3% central confidence interval for the parameter theta. The interval boundaries are points at which the log likelihood function value decreases by 1/2 from the maximum value. This prescription is often used in an approximation of the 68.3% central confidence interval, even in situations when the probability density function for theta hat is not Gaussian and the likelihood function is not perfectly parabolic. Both the probability density function and the likelihood might be asymmetric, and therefore we study the endpoints of the interval separately. Log L of theta hat plus sigma hat plus equals to log L max minus 1/2, and log L theta hat minus sigma hat minus equals to log L max minus 1/2. The numbers sigma hat plus minus are often called asymmetric uncertainties, and the corresponding asymmetric interval is simply theta hat minus sigma hat minus theta hat plus sigma hat plus. A common way how to communicate an experiment result is to quote the maximum likelihood estimator and the up and down uncertainties as theta hat plus sigma hat plus minus sigma hat minus. If we have more than one parameter of interest, then the probability density function of their estimators approaches an n-dimensional Gaussian and a large dataset limit. We construct confidence region in a way that's completely analogous to the one-dimensional case. The construction was already described in the video about the interval estimation. Recall that the n-dimensional Gaussian function is proportional to the factor e to the power of minus 1/2 q of theta vector hat theta vector, where q is defined as q of theta vector hat theta equals to double sum over ij of theta hat I minus theta I times v hat inverse ij times theta hat j minus theta j. The confidence region is determined as a set of points for which the quantity q is lower than some predefined value q gamma. Remember that q is distributed according to the chi-square probability density function with the number of degrees of freedom equal to the number of our model parameters. Therefore, the value q gamma is a quantile of the chi-square distribution corresponding to the chosen confidence level gamma. In this table, check quantiles corresponding to 3 common confidence level choices in different dimensions. Note that the more degrees of freedom there are, the flatter the chi-square distribution is, and the higher value of q gamma we get for a fixed confidence level. Now let's go back to the graphical method. Note that the quantity q also appears in our Taylor expansion of the log likelihood function. Well, if you are super careful, you will notice that the order of theta hat and theta is different, but because the formula is quadratic, it doesn't matter. so it's the same Q as we have in the log likelihood expansion. As a consequence of this, in a large dataset limit, we can construct the boundary of the confidence region at the confidence level gamma using the following formula. Log L of theta vector hat plus delta theta vector equal to log L max minus Q gamma over 2. In 2 dimensions, this equation describes an ellipse centered around the likelihood maximum theta vector hat. It is important to note that, as in the 1D case, people often use the graphical method even if the probability density function for the parameter estimators is not perfectly Gaussian. In that case, the resulting region of the parameter space is just an approximation of desired confidence region. In particle physics, a heavily used implementation of this confidence region estimate is provided by the routine MINOS of the roots minimizer minuit2. Let's stress once again that the region constructed in this way is just an estimate of the confidence region. In case of doubts about the region's coverage, you should do a check, ideally with the use of the Monte Carlo method. Sometimes people don't study the coverage though, and view the likelihood contours as a completely new representation of the statistical uncertainty. Of course, such a representation is not as good as the confidence region because it lacks the quantitative information on the coverage of the 3-parameter values. Typically, the MINOS routine in the minuit2 uses the value of Q gamma equal to 1 when estimating uncertainty of estimators using the graphical method, regardless of how many parameters one has in one's model. This means that the coverage probability of the likelihood contour or hypersurface decreases with the increasing number of parameters. However, such a contour can still be viewed as a graphical representation of the covariance matrix of the maximum likelihood estimators. If there are more model parameters, people often wonder about uncertainty intervals on the individual parameters. For each parameter, the question is, what would be the confidence interval estimate for this parameter if we don't care about the other parameters? The solution is clear. We replace the other parameters by their maximum likelihood estimators. There's one caveat, however. The maximum likelihood estimators are different for different values of our parameter of interest. To take this fact into account, we typically build a one-dimensional likelihood, a function of our parameter of interest, in the following way. For each value of our parameter of interest, the value of the one-dimensional likelihood is the maximum of the n-1-dimensional likelihood that is treated as a function of the remaining model parameters. Said mathematically, log L of theta I equals to maximum over theta j for all j that don't equal to I of log L theta vector. This curve is the famous profile likelihood function of the parameter theta I. We can also say all this less rigorously but more comprehensively. Estimate of confidence interval for individual model parameters are given by a box enclosing a likelihood contour or hypersurface. This is crystal clear in 2 dimensions, where we just draw a box around the contour. As a final remark, it's worth pointing out that one has to use a likelihood contour corresponding to Q gamma equal to 1 to get the uncertainty of individual parameters. Since this is a default value used by minuit2 and therefore also by root, you can rest assured that your one-dimensional uncertainties of the estimated parameters are defined reasonably. It's when you want to draw the contour itself that you have to be careful. If you use the standard settings, you should know that the contour will cover the true value less than in 68.3% when you fit more than one parameter.